All right. So, as George just said, I'm Julian Cohen, here from Eaton in Detroit in the US, and I'm talking to you about how to build a robust metal additive manufacturing process. I'm going to give you a little bit about myself, a little bit more detail on about Eaton, and then we'll kind of get into the meat of why you're actually here. So I'm the lead engineer at Eaton Labs, which is the corporate R&D part of Eaton, at the Additive Manufacturing Center of Excellence, which is where Eaton is doing all of its additive activities right now. Previously, I was an application engineer at Stratasys Direct Manufacturing, worked on aerospace, energy, turbo machinery applications. And previously, I got my Master's of Science in Mechanical Engineering at the University of Texas at Austin. You can see a little bit of my thesis research on heat exchangers for additive manufacturing there, and 5 years of experience in metal additive manufacturing. So a little bit about Eaton. You can see kind of all of the different parts of the engineering world that we were in. We do a lot around electronics and electricity, and a lot around heavy industry, tons of different industries that we are in. And kind of general overview, 21.6 billion in sales last year, headquartered in Ireland, definitely not for tax purposes. And most of our sales is in electronics or in the electrical sector. So we do a lot of CPD protection in terms of like large, talking about sports stadiums and large warehouses and kind of doing breaker protection there. In our industrial sector, we do hydraulics, vehicle filtration, and our aerospace units. So as part of the metal additive manufacturing kind of initiative at Eaton, we're mostly working with our aerospace division. And so I'm going to be talking primarily about what we've been doing with aerospace here. So additive at Eaton, essentially launched in 2016. In 2018, we got our AS9100D certification, which is an aerospace quality certification so that we can actually make parts for flight to actually go on planes. And we currently have 3 active aerospace production programs. So at the COE, we do TRL 1 through 9, so that's technology readiness level 1 through 9, going all the way from kind of base level material characterization and development, all the way through process development and up through manufacturing scale up to final end use parts. And kind of getting more into the details, I'm not going to go too deep into this, but essentially 2011 to 2015, we're doing what everyone does when they start with additive. You know, you're making manufacturing floor products, prototypes, jigs and fixtures, everything like that. Over the last 3 years, we've opened the COE and taken it to where we are now, which is we have 3 awards, 2 commercial and 1 military. The military award is for AIDC, it's a Taiwanese company, and one of our commercial awards, I can actually tell you this now, I'm happy to say, is with Airbus. And we are producing end-use parts that will go on planes, right? They will be flying by the end of this year, actually. And I'm actually in the unique position of not really being here to sell you anything, right? Eaton is making parts for its customers. We kind of have our own initiatives within the company. So, I mean, you know, if you'd like to work with Eaton, please come talk to me. But mostly I'm here to talk to you about how do you scale up metal additive manufacturing to make end-use parts for aerospace. And so I'm going to talk to you about the powder bed fusion process. I think most people here are a little bit familiar with that. And I'll talk to you about the additive value stream, and this will kind of inform the rest of the discussion today. The additive value stream in terms of what does that mean for prototyping and what does it mean for full production? And then I'll go a little bit deep, since we only have a half hour, into a couple of the different points along that value stream. So powder bed fusion, in this case laser powder bed fusion. Also another point, I was informed by the legal team at Eaton that I couldn't use any copyrighted images from the internet, so I've recreated a lot of these images just for you guys, because I know you'd appreciate that. So laser powder bed fusion, like most additive processes, it's a layer-based process. You spread a thin layer of powder, across the surface. You hit that with a laser, and you melt one 2D layer of a part into the previously melted layers, and you build up a part layer by layer in that manner. You get all of the same things you get from all the other additive processes, which is almost free complexity. You can do internal passages, optimize structures, shorter lead times since it's toolless, reduced development and production overhead, and you get smaller bills of materials and assembly times. So now looking at the additive value stream, and this is kind of the crux of what I'm talking about here, right? In the current state of things in 2019, if you have the capital, anyone can go out and buy a metal powder bed machine and make parts, and make good parts. The OEM of that machine, whether it's Renishaw or SLM or any of those companies, they'll sell you the powder, they'll give you the parameter sets, right, for that powder and machine combination, and you'll make good parts, right? So if you're making tooling, if you're making fixtures for your manufacturing floor, it's not going to be difficult, right? You will design the part, you'll print that part, maybe there's some post-processing, some machining to hit final dimensions, and you'll have that part on the floor. And you can do that fairly repeatably, right? When you're talking about getting into serial production, especially for critical industries, so talking about biomedical, talking about aerospace, maybe turbo machinery or energy industries, it is not a linear progression to go from one part to making hundreds or thousands or tens of thousands of parts, and to be able to do that consistently and repeatably. So again, I'm not going to go into all these points, but trying to give you an idea of what you have to start thinking about when you go into production, right? Starting from part different. So how do you know, looking at Eaton, we have hundreds of thousands of parts that we make. Some are cast, some are machined, some are forged. How do you even go about looking at which of those parts should be made additively, right? Most engineering organizations are not equipped to go through that selection process. It requires some additive specific knowledge. The design part of it, if you heard maybe Peter's presentation earlier, to design generatively to consolidate parts, again, requires some additive experience. The pre-print process, going into the actual print process, and then process development, post-process, and quality, the barrier for these is significantly higher than just kind of making one-off parts. So a couple things I want to take from this slide is that the print process, actually putting a part of the machine, is actually one of the least important parts of this whole process. You're going to spend less money and less time on that than most of these other pre and kind of post processes. And another thing is that for production versus prototyping, process development becomes very important, right? You may have application-specific geometries or features, maybe thin walls, that require you to actually develop your parameter sets to make those parts well. So this becomes an iterative process of process development and printing, and that takes time and money that most people are not used to in the kind of prototyping tooling work stream. So now diving a little bit deeper into some of these individual points. Talking about the additive design process, and if you take only one thing from my entire presentation today, please take this: inject additive manufacturing experience as far upstream as possible in the process. Many times we get parts at the AMCOE where I work from parts of Eaton where it's essentially a part that's been made traditionally. It's either been cast or it's been machined, and they say, can you print this? And the answer is, well, yes, we can print anything, but does it make sense to print this? It's probably going to be more expensive. It's not going to be better in terms of material properties. So if you inject additive experience upstream in the process, in the design phase, now you can make parts that are lighter, that are cheaper, that are more effective or optimized for the application that they're for. And it also requires multidisciplinary teams, because when you're talking about creating an additive part in metal that has supports on it, right? How are you removing those supports? Can you remove the supports in a way that doesn't add a step in manufacturing, right? Can you add supports, and can you add post-processing steps that doesn't add to the quality kind of overhead that you have on this part? So if you wait until you've already designed the part to bring in your quality and your manufacturing and your post-processing specialists, essentially, you're losing potential efficiency gains and optimization on that part. And really the point being is that small design changes and small inputs from these experienced people can have large effects downstream in terms of time, in terms of cost, and in terms of process efficiency. And most design engineering organizations are not equipped for these next generation workflows. So again, you saw in Peter's presentation, you've probably seen it multiple places in this conference, we have incredible generative design tools. We have incredible ways to do inline simulation, to iterate on your design. Most design engineers don't know how to do this. And most design engineering organizations are not equipped to do anything other than really design a part in a parametric CAD program like SolidWorks, and then create a 2D drawing based on that and send that to whatever manufacturing organization that they're working with. So again, try and inject this additive experience as far upstream as possible. And so, case in point from Eaton, I'm actually really excited to be able to share this with you. We announced this part at the Paris Air Show last week, so I actually didn't think I would be able to. This part that we're looking at here, which is in the as-built state, is a ram air valve assembly for the AIDC Corporation, which is Aerospace Innovation Defense Corporation, something similar to Taiwanese corporation. This is actually an assembly. This part actually goes into kind of the hole here. It's machined and there's electronics added. It is on the outside of a jet, and it opens in the event of emergency and allows air intake into the cabin. So we reduced development time by 75%, consolidated 22 parts into one additive component, and that eliminates seals, it eliminates threaded joints, and it eliminates potential leak paths, right, for this part that's on the outside of a plane. And we reduced part weight by 10%, right? These things are not possible if you just take the original design and simply try to 3D print it, right? You need to actually change that design and optimize it for the process. There's another part that I would love to be able to share with you. I can't right now, but look for that in the very near future. So now talking about digital thread. This is a buzzword that you've probably heard at this conference before. And the digital thread is basically the fact that when you take an additive manufactured part, it's not just the part sitting on the table. That part is actually one node in a long thread of digital manufacturing that has occurred both before you've made the part and once you put it in the field. And again, most engineering organizations are not equipped to kind of deal with the amount of digital data that is created and that must be archived during this process. Looking at aerospace specifically, what we're doing here, traceability is a serious concern in aerospace, right? And traceability both ways. So if a part fails in the field, look at the Boeing aircraft, right? If a part fails in the field, you need to be able to understand what build off the printer that came from, what powder lot did that build use, and what original lot of material did that powder come from. And going the other way, if you find out that one powder lot of material that you used to build your parts was bad for some reason, the chemistry was off or the powder size distribution was off, you need to be able to go into your software essentially and know every single part that you've made that came from that powder lot. So looking at this thread basically through all of these nodes, it starts in design, goes through kind of the parametric CAD and the drawings and tolerancing, through simulation and analysis, design iteration, parameter development, part development and testing, support design, build layout, additive process, into your application-specific processes for that part, and then into kind of the quality and inspection applications that you're doing. Now the part's in the field, you may have sensors on it, you may have data coming out, there's maintenance, there's inspection and repair, and eventually part end of life when it's retired. So the data that coming out from this whole process could be hundreds of gigabytes, it could be terabytes. If you're looking at in situ monitoring on your metal machines, it's definitely terabytes of data. So how do you store that? How do you access it? And how do you ensure that, for example, if you're putting a part on a plane that is going to be in the air for 20 years, how can you access that data in 15 years when no one that worked on the part originally even works at your company anymore? It's difficult to design robust processes to actually ensure that this is possible for your customers. And kind of as just one point in the digital thread discussion, I have vector versus raster here. If you've worked in 2D images in Photoshop or graphics or anything, basically a vector is something that is defined mathematically, and a raster is something that is defined as like a bitmap. And the analogy here is something that you design in a CAD program like SolidWorks, where a sphere is mathematically defined, right? It's a sphere, versus when you export to an STL, what you get is a triangulated mesh, right? And I hate STLs. I hope that they become completely irrelevant to the additive manufacturing process, and I hope that this slide is irrelevant for everyone here in a couple of years. Right now, in many of the workflows, if you use Materialize Magics and some of the other programs, you have to use STLs. So the question then is, how do you control this conversion from a mathematical object, right, a surface-defined parametric CAD object, to what is essentially a bitmap, more or less, right? It's a triangular mesh. If you were to try and 3D print a sphere like this, you'd probably see the facets on it, and you'd understand that, wow, I probably should have exported a higher quality object. But the difference between these two objects, maybe you can't see that when you print it. But do the edges that you've created in this STL, do they affect the fatigue life of your object, right? Do they affect maybe the fluid flow around a roughness on your surface? And then you also have, again, the data management, right? So this is 25 megabytes, this is 100 kilobytes. And if you're printing 100 of these on a plate, that you've now kind of exponentially increased the amount of data that you have to store and access again through the whole lifetime of the part. So, and since there are so many CAD packages, right, you have SolidWorks, NX, Creo, all the different packages, and they all export STLs in slightly different ways. How do you as an organization control this export to an STL? And then how do you measure and how do you validate the export? I've worked with many design engineers at my current role in Eaton and at Stratasys Direct where I asked them, how many facets do you have on this mesh, or do you know at what quality you've exported the mesh? And they said, I have no idea. I don't know. I don't even know how to measure that or how to go back and find out what I exported it as. So now, looking at the actual additive manufacturing process itself, there are analogous processes where the way that you're making the part affects the material properties. Looking at casting, right? The way you cast the part determines the type of porosity. Or looking at metal injection molding, the way that you've done that process, the amount of pressure, the amount of heat, that determines the part. But in laser powder bed fusion, the key is that the process is the material. And the manufacturing process creates both the geometry and the material properties simultaneously, right? Looking at the process itself, this is kind of the details of the laser powder bed process. It's very dynamic, it's very chaotic, and it's very stochastic, which means that you get slightly different results every time, and it means you have to control this process very well in order to get the same part every time, right? You have slightly different distributions of particle sizes and kind of gaps in the powder bed itself. When the laser comes down and hits and creates this melt pool, you have a cavity here, which is actually a depression in the melt pool. The liquid in the melt pool is recirculating to a Maragini flow. You have a solidification front. You have a vapor plume coming off and throwing powder into the air. You have particles of spatter particles, which are kind of partially melted, flying out the other way. So, and actually you can see, I don't have this on here, but you can see in some of the more recent papers coming out of, I think it's Lawrence Livermore National Labs, they have a synchrotron, and you can see this process happening in real time in slow motion. And it's very chaotic. So the question is, how do you make sure that this happens the same way every time? And it comes to process sensitivity. And what that means is, if you, for example, if the laser power changes by 1%, what does that mean for your process? Does that mean it's a bad part? Can you deal with a 1% change in laser power? And can you do that for scan speed, spot size, layer thickness, raw material, and gas flow? And so controlling all of these individual inputs into the process becomes critical to actually make good parts repeatably. And kind of just to drive this point home, if you work in this industry, you've probably seen this before. This is called a PV map or a PV space, PV being power and velocity. And this is essentially a 2D representation of a response surface of what is actually happening in the powder bed fusion process. So on the vertical axis, you have laser power, and on the horizontal axis, you have scanning velocity. And this is basically how you determine, or one of the ways you determine your process sensitivity from two of the kind of main inputs into the process, which are power and velocity. So if you put too much power into the part and don't go fast enough, that depression in the melt pool actually goes too far deep here, and you get holes, porosity in the part because you put too much power in. If you don't put enough power in and you go too fast, you get lack of fusion, right? You have unmelted particles in your part. And if you go too fast with too much power, I don't have an image here, but you basically, instead of a single track of melted powder, it kind of balls up, and you get like a nonlinear melt pool. So in general, people want to be in the conduction mode zone, which is this triangle here, right? So, and you want to build as quickly as possible. So most people will try to have their parameter set around here, right? Which is great, because then if your laser power changes 1%, you're still within that good zone, right? But if you're running a parameter set and you're not sure where you are, and you're near the edge here, and your velocity changes because your galvanometer does something wrong, well, now you're creating keyholes in your part. And then the question is, as I'll talk about in 1 second, how do you deal with that keyhole? How do you find out where it is, and how do you inspect that part? So it's critical to understand kind of where you are in this PV space and what the process sensitivity is if you want to make these good parts repeatably. And actually, so for that presentation, or that paper, you can check that out. So now talking about industry maturity in general, I think someone said during the keynote, I believe from GE Additive, that metal is lagging behind plastic or polymers in the additive space in terms of where it is on that maturity curve. So right now in the metal industry, it's still very immature, right? And what that means is you get cautious customers. So when Eaton, for example, when we work with the Airbuses or the Boeings or the Lockheed Martins or whoever of the world, they're extremely cautious with metal powder bed processes, far more than they would be with any traditional process. And it's kind of a vicious cycle where, if you want to go to a design engineer and have them design a part for you, the first thing they're going to ask you for is, okay, give me my material allowables, right? What's the ultimate tensile strength? What's the fatigue life of the material we're working with? As I said previously, the process that you're using is creating the material, right? So there isn't really any standard material design data, right? There's no textbook to go to or industry site that'll tell you, here's the ultimate tensile strength of your aluminum silicon 10, for example. And then as a result of that, companies like GE Additive and like Stryker and like other large companies spend a lot of time and a lot of money developing their material knowledge and doing material development. And it's shockingly time consuming and expensive is how I'll describe that. So obviously these companies want to keep that information close to the chest, right? They're not going to tell anyone about the data that they've spent millions and millions of dollars and years to gather. So they protect their IP, and what that means is that industry standards are slow to emerge, right? These companies don't want to work together. And there are some governmental programs, at least in America. There's America Makes, which tries to put money grants out there to bring companies and universities together to generate this data. But again, very difficult. These companies are kind of slow to interact with these programs. So it's a vicious cycle where the data doesn't exist and people have no way to get the data. So I don't know how to break this process. I'd love for the companies to be able to work together. But the bottom line is that when you go to an end-use customer and tell them we want to use laser powder bed fusion or metal additive to make this part, the hurdles you're going to have to jump over in terms of their confidence and proving to them that the part will perform as it should is going to be extremely high, because in their eyes the risk is just very high. So now talking about quality for a moment. So for traditional processes like casting, again, it kind of goes back to the earlier point, there are standards for how to inspect the parts, and there are standards for what to look for in those inspection processes. In metal powder bed, we don't really know, or we don't have industry standards in terms of what to look for. We do know that the types of defects that you get in the laser powder bed process are different than what you get in casting, for example. In casting, you get spherical pores. They might be large, they might be horrifyingly large, like if you looked at a casting, but they're spherical and they don't really create stress razors. In metal powder bed, you can get weird, jagged pores. You can also get gas porosity, but pores like this due to lack of fusion or keyholing, where they do create stress razors, and we're not necessarily sure how that affects the fatigue life, for example, of the material. So, from this massive suite of types of inspections that we have in the industry, right? There's non-destructive options like X-ray CT, which you can see here. It creates a 3D representation of the part, including any pores, for example, in red and blue there. And this is a really incredible technology. If you're a GE Additive, then you've invested in companies that make CT scanning machines. But for most of us, it's incredibly expensive, it's time-consuming, and depending on how you scan your part determines what size of pore you can find. And so this is not necessarily a sustainable process for production of your parts if you're making thousands of your parts in terms of the cost it adds per part. So then maybe you can go to X-ray radiography, to do an X-ray. And what this gives you is basically it's essentially a 2D slice of a CT, where a CT is many X-ray slices built up. And from a 2D image like this, you can look at the grayscale formation, and that can tell you a lot about the pore structure and the potential defects in the part. But we also know that depending on how you do your X-ray, you might not be able to catch the small size of pore that you find in a metal part. And then in terms of destructive, right, the standard process is you take your part, you cut it up, mount it, and polish it. You can look at and then etch it, and you can look at the melt pools, you can look at the pores, and that's fantastic. But how can you be sure that the slice of the part that you're getting is representative of the whole part, or that you're catching pores in critical locations? And you can do a similar thing with electron microscopy or visual microscopy and looking at kind of this formation. But kind of the bottom line is among all of these different inspection processes, what is the correct one to use and what makes sense to use for your application? And if you have someone who's an experienced additive designer or manufacturer, great, maybe they have some experience in terms of what they have done. But is there a central location or an industry standard to where you can go to look up what to use here? And the answer is no, unfortunately. So kind of as a bottom line, we don't really know how to look for what we need to look for. And that is something that is kind of a tribal knowledge built up in individual companies. And again, I don't know what the answer is, but I think we need to create these industry standards to look at and create and look for these different defects. And then just kind of as a finer point on quality, geometry as well. So the material can have all these defects, but how do you look at the kind of bulk quality of your part? I've here an image of SpaceX because they famously print their Super Draco engines in 2 parts and then laser weld them together. All the different space companies or the private space companies are doing something similar. This is not a SpaceX engine, it's kind of something I'm doing on the side, but they use regenerative cooling with these kind of internal cooling lines, right? So first things first, how do you remove the powder and how do you ensure that the powder is fully removed, right? If you take a part with powder still left on the walls and you put it through a heat treat cycle, that powder can sinter to the walls, and now you have risk of FOD, which is foreign object debris, flying off into your fuel line and causing damage to the part. And aerospace companies take this extremely seriously. How do you ensure geometric accuracy so that the wall thickness that you've put through your finite element analysis, that you've done all your stress analysis on, how do you make sure that that's actually accurate, right? That the wall is not too thin. And how do you ensure that the surface finish in these internal passages is good, right? We know that the angle changes the surface finish depending on the angle of how you build it. So, and that's going to affect both the fluid flow and the fatigue life of that part. So these are all fairly open questions in the industry, and I don't have any answers right now, but these are the kind of things that you have to think about when you go into production on these metal parts. And that's all I have today. I'd love to get into more detail. Please find me later if I don't get to it in the question and answer session. And I have a work email and a personal email there to talk to me. So thank you very much.
시간이 조금 여유가 있어서 질문을 한 분에게 2분 정도 받아보려고 하는데 혹시 질문이 있으시면 손을 들어주시면 제가 마이크를 접해드리겠습니다.
Any questions?
I may ask one.
Please.
Yeah. So a good observation about the impacts of voids or lack of fusion or any anomalies that we usually consider detrimental for the properties. The question is, you guys at Eaton, have you looked at the effect of these anomalies in your properties? And what kind of properties do you envision? Because the experience that we have is it depends on the material, it depends on the property, then you may still tolerate some level of presence of these anomalies in your system.
Yep.
And that makes the standardization way different and difficult. It's not casting, it's not forging, it really depends on material application and a process.
Mm-hmm. Yeah, I mean, it's a great question. You went into some detail about this morning in your keynote, and Eaton has actually worked with GE Additive fairly extensively. So, and I guess to answer that, I mean, look at casting specifications, right? For grade, I don't know if it's ABC or 1, 2, 3 castings. The level of defect that is allowable, even in critical parts, is compared to what I'm used to, is horrifying. They're very large, and you allow a lot of them. So to your point. Eaton has done a fairly extensive amount of work in terms of material characterization and understanding what we're getting out of our process. We have what we term qualified metallurgical process, which is the combination of the material, so the powder feedstock, the parameter set, which is all of the laser parameters and machine parameters, so basically everything that goes into creating the part and for a specific application, and basically what you can allow for a specific application is not going to be the same as for another. So it's, I guess to your point, I don't have a really good answer. It is very difficult to define, and I think from my perspective, is it possible to create more general specifications? Can you make an aluminum, silicon, 10 magnesium for rotating parts specification? And I hope so is the answer, but right now I'm not sure. Yeah.
Julian, have you ever considered the impregnation system for metals to seal those crack formations or porosities?
So the question is have I considered impregnation methods, basically where you take what the part you've made and you impregnate that with a different type of metal, if I understand correctly. So obviously there's some kind of metal methods that do this, right, where you create a part and then you impregnate it with another metal. One of the issues is that many of these pores are not surface connected pores, so they're internal to the part, and there isn't really a way for that metal to impregnate into the part. There's a process called HIP, which is hot isostatic pressing, which is fairly standard in powder metallurgy, that you put a part basically in an oven and at a high pressure, and it closes any non-surface connected pores. It basically just forces the material isostatically to compress. And most aerospace parts, certainly for space, go through a HIP process, and it does do a very good job of closing most of those pores. There are open questions around what happens to those pores in fatigue, whether they reopen or what type of pressure is in those pores once they've closed. So I guess, actually, so to answer your questions very shortly, no, we haven't really considered it, but I'm not sure how well it would work for these parts. Yeah. Yes?
Yeah, I hope I didn't miss this point in your introduction, but what's actually the goal of Eaton? Do you actually want to make like a standard for 3D metal that you can say, okay, well, for these parts we are allowing these tolerances, these control checks, or does it always have to be looked at individually, design for design?
So broadly, Eaton's goal. So our aerospace division makes parts and then assemblies of these parts that we sell to the kind of aerospace primes like Airbus and like Boeing. So Eaton's goal broadly is how do we inject as much additive manufacturing as possible where it makes sense into our aerospace portfolio. There's tons of casting replacements, for example, that can be done well with additive. And from my perspective within Eaton, we'd like to generalize as much as possible. So we do create these qualified metallurgical processes. For example, right now with aluminum, silicon, tin, magnesium is the main material we're working with, among some others. We do have standards about what we expect to get out of the material in terms of bulk properties, like ultimate tensile strength, elongation break, those kind of general mechanical properties. And so generalize as much as possible, and then where necessary, get application specific, and whether that means internal geometries or thin walls or whatever's required for that application. Anything else? All right, thank you very much.